topic of discussion, what all we are covering is classification of visible surface detection algorithm for detection or the depth buffer. So these are the three topics we are going to cover today. What is a visible surface detection? So you can see a two picture here, a left and right side, two pictures. Left side, you can see there is an objects. There are too many objects. There's too many objects. Some objects are visible. The obvious left side includes a blending function, which is not there in our syllabus. And that's nothing but your alpha value, fourth value in GL color, clear color, alpha value, which gives you the transparency. Fine, that's a blending function. So we are not dealing with that. But here we are checking here, you can see it's a green object. Behind that there is one jug. Some part of the jug is actually invisible. So that means this green object is actually covered the jug, some part of that. So like that, you can see a jug. So that means when you have too many objects on the scene, especially in 3D, the 3 dimensions, some objects will not be seen and some objects will be seen. So that is what here we need to detect which part of the object is visible and which part of the object is not visible. That is what we are trying to detect here. In the right side we have a 3 mobile. You can see the 3 mobile right side. The some part of this mobile, the first part is completely seen, and the second part, it's only a 3/4 is seen. 1/4 is overlapped by the first mobile. So like that in the third mobile. So if this is the case, why will I draw the complete, what I can say, object, the second object or the third object? Why will I completely draw? I don't have to draw. You can come back to the left side image. There are two, obviously, in our case, we don't have a blending function, or we assume that is complete. Behind, you can see a 2 small glasses, which is actually completely almost covered. So when we don't have a transparency and we are only checking with the visible surface, why will I draw the previous objects which is not seen? I should not draw it which is not seen. So before drawing itself, I need to detect which surface or which polygon surface or an object is seen, visible and not visible. And only the visible objects will be drawn further. Fine. So that is the major thing we are learning today. So now we'll now see the visible surface algorithms. So what is visible surface algorithms? Obviously a major consideration in the generation of realistic. So obviously I will say it is a realistic graphics displays to make it more realistic, right? In determining what is visible within the scene from a chosen viewing position, I should be very careful that they have told here it is from the viewing position, chosen viewing position. Based on the viewing position, the visible surface will get changed. Fine, you agree with that? If I see from the front, my view of a visible surface might be different. If I see from the side angle, there I can see other objects which was hidden from my previous view, and might be some other objects is hidden which was seen visible from my previous view. So that means based on the viewing position, my visible surface will be detected. So all this led to intense interest in finding efficient algorithms for visible surface algorithms. So all this made actually efficiently identify the algorithms for visible surface detection. So now this visible surface algorithms is also called as hidden surface removal, visible surface detection, or an algorithm. We call it as a visible surface detection or hidden surface removal. Whichever the surfaces is hidden, I have to remove that. Which are the surfaces are visible, I need to detect that. So these are the two names is given for the same kind of an algorithms. Both can be called. So that saying two names are used interchangeably. Many were generated during the period of intense interest around 60s and 70s. All these algorithms were identified. Visibility of primitives. Now, what is a primitives? Primitives is a basic objects drawing. While when I draw a primitives for the objects, what are the criteria that I have to identify here? We don't want to waste time rendering primitives which do not contribute to the final image. When at the time of projecting onto the final screen, my final scene or a screen is nothing but a device, right? At the time of projecting, why will I draw all the primitives or an image which is not seen also, right? So a scene primitive can be invisible for three reasons. What are the three reasons is invisible? Primitives lies outside field of view, right? Primitive can be field of view. That's nothing but my clipping window. It is completely out of my clipping window. Then why will I keep drawing in all my coordinate systems? Next, primitive is back facing. It's completely back facing and we are not able to identify the object under certain conditions. The conditions can be anything. Then why will I project those objects? Then primitives is occluded by one or more objects nearer the viewer. So that is nothing but object is overlapped and it is not seen because of the objects which is overlapped by the nearer objects from the viewpoint. Then why will I draw that object which is completely covered behind some object? So why will I draw that object? So there are the three scenarios where I need to avoid drawing my primitives in such conditions, in all these three conditions. Then, now my main thing is how do we remove these efficiently and how do we identify this efficiently? How do I identify these efficiently? Is my main goal now, further what we are trying to see. Now, let us see the visibility problem here. Clipping, obviously, if it is out of the view, then I call it as I use a clipping algorithm, which we have already seen. My view is now only this much. My view is only this much. If I see any object drawn here, then why will I draw this object? So I have to clip it. So I'm clipping that in the initial stage itself, right? So we are using clipping algorithm. So there are two problems remains. What is a true problem? The first problem says removal of faces facing away from the viewer. If you have any image is very away. Now you can see here. It's completely dark. Might be there is something else. So I have to remove those. I don't have to project if there is an object away from my viewing point, which I'm not able to identify that object. Then we will see that we will not face that object. Next, second part is removal of faces obscured by closer object. Obviously, if something is behind some objects, behind these objects, which is not at all seen, then I have to not write that. I have to not draw that objects. Now you see here, the left diagram is actually shows you the wireframe of the objects. So the wireframe gives you the overlapping or occluded images also I can see here. There is a tire kind of or torus we call it as kind of an image, wired torus, and then it is actually occluded on the or overlapped on the cube. On the same way, you have a jug, and this is too much complicated. And behind this, I have something here, and the lines I could see here. I mean, that's a lamp I could see, and the line. So everything is drawn here. Everything is drawn. Now, from this part, I have come to the right part, right side. Now, whichever the part is not seen, see, this is actually behind the square cube. So what I'll do this when I draw it as a solid object. So there's nothing but that part I'm not drawing here. Fine, that part I'm not drawing here. So this is, so you can see here. So here also some object, some part of the object is invisible, right? Or hidden, I can say. I can also say it as a hidden. So like this, the objects need to be taken care, or which kind of an object should be removed. So that we have discussed here. Now we will see with respect to the algorithms. So we can classify the visible surface detection algorithms in two ways. Broadly classify visible surface detection algorithm according to whether the object, they deal with the object definition or with their projected image. The classification of visible surface detection based on the two things. One is object and one is image. Fine. So these two approaches are called object space methods based on the based on the concept of object, or on the object concept we are going to deal with this, and image space. Okay, and image space methods respectively. So these two approaches are called object space methods and image space methods respectively. An object space method compares objects and parts of objects to each other within the same definition to determine which surfaces as a whole we should label as visible. Okay. Based on the object or parts of the object, we derive an algorithm to determine which surfaces as a whole we should label as visible. So in an image space algorithm, visibility is decided point by point at each pixel position on the projection plane. So in an image space algorithm, visibility is decided point by point, as that's nothing but based on the pixel. So in image is actually, it's based on the pixel. Here in object, it is based on the object or parts of the objects. Based on the parts of the objects we consider. We will see how is it. So these two different type of algorithm we will discuss today. It's the same algorithm. We will take the picture later. Now, the first kind of an algorithm is algorithms. One example with respect to object space method and one example with respect to image space method. Fine. Backface detection is my first algorithm. Now, a fast and simple. So this algorithm is an example for object space method. For locating the back faces, so that is nothing but a hidden face. So this algorithm mainly deal with for locating the hidden faces of a polyhedron is based on the front back test. I don't know whether you remember the front back test that we have done in the first module. We have a front back test. I'll just give you a glance of front back test. What happens with respect to the front back test? For any point XYZ not on a plane with parameters A, B, C, D is a plane parameters. Okay, it's a polygon, any kind of a plane parameters, a boundary of a plane. That gives my ABCD. We have AX plus BY plus CZ plus D is not equal to 0. If this is equals to 0, then the point is on the plane. So then the point is on the plane. If this is not equal to 0, then I have, the point is not on the plane. Then I have a two scenarios. So what is the two scenarios? The two scenarios says ax plus by plus cz plus d is less than 0. This ax plus by plus cz plus d is equal to 0 is actually a plane equation. Hope you remember, which you would have learned in the maths. It is a planar equation. Okay, it's a plane equation itself. So if it is less than 0, then the point xyz is behind the plane. If ax by this equation is greater than 0, then the point xyz is in front of the plane. So which one I have to take now? I have to take this one, this equation to solve, to identify the backface detection, right? So this two is nothing but my front back test. A point xyz is behind a polygon surface if ax plus by plus cz plus d is less than 0, where a, b, c, d are the plane parameters for the polygon. So we have already checked that also, right? The convex and concave polygons. What happens if it is a convex polygon? What happens if it is a concave polygon? So everything we deal with, either the triangle is also called as a polygon, right? All our wired frame, you can see it is split into a multiple polygons, so that filling the color, everything will be easy. So any kind of an test, even in your visible surface detection method also, we use a polygon to identify it, what I can say, easily. It will be easy to identify. Fine. So what is this? So this is one method, is actually nothing but your plane equation, by using a plane equation. Fine. There is one more method that is nothing but, it's a more simplified one. We can simplify the back face test by considering the direction of the normal vector n for a polygon surface. So this is one more very simple way. So you can check here. You can see here, this is my view, this is my V, this is my V view, fine. That is nothing but in which direction I am seeing the object. This is my object. Now, if I want to decide this face, whether it is front or a back face, my normal vector will be like this, fine. My normal vector will be like this. If this is, the normal vector comes like this. For any face, however you place your, what I can say, your right hand or left hand on the surface, and see how vertically you keep your thumb from the surface, in which direction the thumb shows, that direction you will draw a normal vector, fine. So this is a normal vector for this. So now for me, accordingly, this face should be a front face. This face should be a back face, right? This face should be a back face. For the viewing direction, which is my viewing direction? This is my viewing direction from the camera. So now, how do I deal with this? It's very simple. Do a dot product, because both are the vector. V is a vector and N is a vector. Do a dot product. Fine. When you do a dot product, if the value will be greater than 0, if the value is greater than 0, then it is back face. It's very simple. Okay, let me bring up our coordinate system. So our coordinate system, I've brought it here. What kind of a coordinate system it is? Left-handed coordinate system, right? Please keep it left-handed coordinate system. Your z-axis will be away from you, fine? So when the z-axis will be away from you, from your eye, okay? So this will be your negative. This will be your negative z-axis. This will be your negative z-axis, right? And where this part is your positive z-axis. Now you see here, this is positive. Where actually your n stands? When this is positive, according to your viewing direction, this is your coordinate system. So when you check with this normal, it is along your z-axis. So your n also will be positive. N also will be positive. When both are positive, obviously when you take a dot product, your it will be greater than 0. Positive will become greater than 0. Fine. But and another case now. The other case now. Now, if a face is front, which is your front side, that this part is your front side, right? This face is your front side. For this viewing direction, the viewing direction is what? Wherever you have a camera. So this viewing direction, this part is your front side. So now, what do you expect your V dot N? It's nothing. See, the object is drawn based on the left-handed coordinate system, right? Left-handed coordinate system. My left-handed coordinate system, it is along the z-axis. It is in the direction of the z-axis. Fine. When you place your object here, your normal vector always will be in the same direction. So whichever is in the same direction, the complete object is drawn based on the left-handed system. So my coordinate values, everything is based on the left-handed system. Fine. So now, when you see a normal vector, along which direction it is going? Along the positive z direction only the normal vector is going. So when along positive direction it is going, I will get a normal vector is positive. The viewing angle is also along the z-axis. I am seeing, keep my viewing here. Okay, let me see, I'm seeing here, my camera is here. So my viewing direction is here. My view is also along the positive direction. And my n is also on the positive direction. I will get positive value. Now you check. N is what? Here. Now, okay, this is a detection of back face. This is detection of back face. Now let us check a front face. Okay. Now, how is the direction? Direction is like this. Direction is like this. Fine. When the direction is opposite to the z axis, when the direction is opposite to the z-axis, that means what? This will become a negative. It is opposite, right? Opposite of positive is what? Negative. So it is opposite to your z-axis. So your view will be less than 0 if it is front size. Because both your z view and normal or view is your viewing vector is always on the z-axis. Always on the z-axis. We have already dealt in the last classes. Now, viewing is in the positive direction of z-axis always, and negative n is coming opposite direction. When it is opposite direction, obviously it will be less than 0, or sometimes it might be equal to 0. So instead of taking the complete values, you take the complete. So what will be your So what will be your value? V, obviously, when you keep your view V here, viewing direction, always it will be like this, viewing direction. So then what happens? 0, 0, VZ. And what is N? N is ABC. Let us consider it as an ABC. That is nothing but it has moved along. How much it has moved along? X-axis, Y-axis, and Z-axis. So what is your Z-axis formula you will get? C. So usually when you do a dot product, ABC will become nil, and VZ dot C only you will get a value. So your major dot product with respect to V dot N is completely relied on the VZ dot C. We have done the dot product also, splitting concave polygons. We have done dot product there also, the formula, using the formula of a dot product. So this is backface detection method. Now we have still one more scenario here. So now we are considering a right-handed viewing system. In the previous slide, we have considered a left-handed viewing system. Now we will see fast what happens with respect to the right-handed coordinate systems. Check with the diagram here. This is now I've considered the right-handed. See, my Z is this side. Okay. So in right-handed system, you can see this diagram. It is a right-handed. On the right-handed, you can see here, your viewing is this side. They're showing your viewing. So that means it's this side is a negative. If your viewing direction is this, then I say my viewing is in which direction it is? My viewing is in the negative Z value. You keep wherever you want your viewing. It is going opposite of Z axis, other it is negative only, right? So now, what will be the C value? It is ulta of our previous left-handed system. Left-handed system, if it is a back face, then it should be greater than 0. When it comes to the right-handed system, my C value should be less than 0, right? So that means my N dot V, if it is less than 0, then if I call it as a back face. Now, this is my normal vector. Sorry. Now, this is my normal vector, which is front face, which is along the direction of x-axis. So where I will get a positive direction. So that means C or V dot N is greater than 0 on that, that we will get a front face. It's exactly ulta, opposite of my left-handed viewing system. So this is one scenario we are discussing here. Now, when it comes, we are still with respect to the object method, space method. When it is an object space method, obviously there is one drawback here, which we call it as a drawbacks of backface culling method. Then what is that actually? See here, see this object here. What is happening with respect to the object? When I take, usually in object space method, polygon, object by object I will take, or a part of the object I will take. Part of the object I will take, and then start deciding which face is front and which face is behind. We will divide this. If it is a convex polygons, we already know if it is a convex, we will divide into multiple concave polygons, right? So we will divide. While dividing, see this face. This face is actually, see, I'll just draw here. Okay, I will draw here. This is a space where some of the portion is already hidden. Which other portion is hidden? This much portion is already hidden here. This much portion is already here hidden. Where this portion only a very less part of the portion is seen, and 3/4 part of that portion is visible, invisible. So in object space, because Object by object we will decide here. The complete one part of an object I will decide, and I will see if I divide this part like this, then if I take somewhere a C comes, then my normal vector usually comes from the middle. My normal vector comes for the middle for this face. So usually I will get what? It is hidden, right? It is hidden based on my viewing angle. Assume your viewing angle is whatever your camera, because based on that only I've drawn the diagram now. So now, according to that, we assume that this face is completely hidden, but there is some part which is actually seen. So this is actually a problem to identify in our back face detection algorithm. Okay, this is actually a drawback here. So that means some part. So what? I have to do a more test. Apart from this, I have to go ahead with an additional test to identify the additional faces that are totally or partially obscured. It is hidden. Now, after identifying which face is back face and front face, after by using an object space method, on top of that, I have to go ahead with one more algorithm saying that is this face is totally hidden or partially hidden. I have to go ahead with one more algorithm to detect this. So this is a drawback we are finding here. Fine. Now, the next algorithm. Next, a depth buffer method. So depth buffer method is based on the image space approach. Fine. Detecting visible surface. Here we are detecting a visible surface. Okay. That was a hidden surface, the previous algorithm. Back face was detecting. The other face, only two face we will have, front and back face, because we will divide into a polygons. We will divide into a polygon there. So here what happens? We will detect a visible surface, okay, which compares image space approaches this, which compares surface depth values throughout the scene for each pixel. So here what we will do, object by object, we are not comparing here, we are comparing with respect to the pixel by pixel on the projection plane. Each surface of a scene is processed separately, one pixel position at a time across the surface. So the algorithm is usually applied to scenes containing only polygon surface because depth values can be computed very quickly and method is easy to implement. Okay, so we will see here the visibility detection approach is also frequently alluded to as a Z buffer method. Why do we call it as a Z buffer method? Because the object depth is usually measured along the Z axis. How do you check the depth? Depth is always with respect to the Z axis. Okay, width is always with respect to the X axis. Height is always with respect to the Y axis. So depth is always with respect to the Z axis. Hope you can analyze that. So now see this diagram here. So when you see this diagram, you can see a point. This is my viewing plane where a camera I'm seeing like this. Okay. So now I'm going along. This is my depth along the Z axis. This is my depth. How many objects you can see here? I could see more than 2 objects. There's 3 objects. We have S1, S2, and S3. Fine. This is my viewing direction. This is my viewing direction. Right? Okay. Okay, this is my viewing direction. This is my viewing direction. So I can see S1, S2, and S3. Now, how do I identify? This is a position with respect to X and Y. Throughout this is my point of X and Y. This is my point of X and Y. If this is X and Y position, that means, let me say, this is 30, 50. This is 30, 50 is my X position. This is 30, 50. If this is 30, 50, on this object also the point is 30, 50 only. This is also 30, 50. This is also 30, 50. Right? All these three objects is lying on the position of 30, 50 with respect to X and Y value. Z value changes here. This Z value might be, this Z value might be so this Z value might be, what will be a Z value for this? Let me say 10, okay? And this Z value might be 20 and this Z value might be 30. So that means all this object is actually placed along the Z axis, but XY is same on all this position. Hope you are understanding this. XY is there. This point, I'm talking with respect to this point, the point what is shown here. Fine. So how do I check with the now depth buffer? Very simple method. Now this is my maximum. Assume this is my maximum, which is maximum is 50. Okay. Assume this is my maximum. So now I'll start comparing from this point. I'll start comparing from this point. On XY position, that is 30, 50. On 30, 50, my Z value is 50. When I come back to this point, my Z value is 30, which is 50, compare 50 and 30, which is less, put it on the position of buffer, XY position 30, Z value. Now come back to this, because compared to this position, 50 position, which is my near position, 30, whichever the object is near to me, that is seen. Away from me will not be seen, right? Because all these three objects is overlapped here. When it is overlapped, only the object which is near to me is seen. Near to me is seen. Away from me is not seen because it has been overlapped by the other objects. Now my Z value is now kept 30 enough. Now come back to the S2. When you come to the S2 XY plane, I have Z value 20. So compared with the S3, 30 is actually more than S2. So that means S2 is near to my viewing plane because Z value is less. So replace Z value to 20. Now S1, it is 10. The previous in that buffer, what is stored? Z20 is stored. Compare these two, which is near, it is 10 is a near. So in this point, for this point on this pixel, which value is stored? S1 value is stored. So that means which object is seen? S1 is seen. This is an overview of the depth buffer method. We will get back to it. If you have any small doubt, we will again view this, visualize this. Okay. So that is the main method of the depth buffer. So based on which actually the depth buffer is done, based on the Z axis. That's why we also call it as a Z buffer method. So many a time they will tell you, they will ask you in the exam with the name of Z buffer method. They keep interchanging the names of the algorithm. So we call it as a Z buffer method. It's the same example. I'll get back to this example later. Now let's see. Now whatever I have told you in brief here with respect to the diagram, the same thing we are going to discuss here. Okay, the same thing we are going to discuss. Let's check here. These surfaces can be processed in any order. Okay, you can start processing in any order, either from behind the far plane or from the near plane, as each surface is processed its depth from the view plane. Depth is actually processed with respect to the view plane, right? So the depth is more when it is away from the view plane. The depth is less when it is near to the view plane. So in the depth is considered based on your view plane only. Based on your view plane. So now if a surface is closer than any previously processed surface, its surface color is calculated and saved along with its depth. So if any surface is closer, so they will calculate what? They will calculate the surface color as well as the depth, and then will save. You will understand that. Implementation of depth buffer algorithm. Implementation of depth buffer algorithm is typically carried out in normalized coordinate system, not in a view coordinate system. Normalized coordinate system, this visible surface detection is actually, algorithm is actually implemented before putting that into the viewport or the screen device coordinate system. So normalized coordinate system, what is your range of your depth? That we know already, all x, y, z range will be 0 to 1 or 1 to -1. So here we are considering near plane, 0 at the near plane, and far plane, how much we will have? 1.0, because it is normalized coordinate system. As implied by the name of this method, 2 buffers. We need 2 buffers for this implementation. We need 2 buffers for this implementation. 2 buffers for this implementations. That is depth buffer and frame buffer. What is depth buffer? Depth buffer will tell me, will keep the information of Z. What do you mean by depth? How do you identify depth? Depth is identified only based on the Z values. So I have a separate depth buffer to store the Z values. Okay. To store the Z values. That's why, you remember or not, whenever you do execute a 3-dimension 3D objects, you will call the enable depth buffer. You have to enable the depth buffer because Z values is stored separately away from the normal buffer, which usually store our XY position. It will not store with this position. Z values is stored separately, only to compare Z values with the buffer algorithms, because depth buffer algorithm I have, which only compares with the Z values. So I keep the Z values there for all the positions. Okay. Now, then we have a frame buffer. Frame buffer I have to store the color values for that particular pixel. Fine. Initially, all positions in the depth buffer are set to 1, and the frame buffer is set to background color. When the object is not at all drawn, fine. Now you assume everything is empty, object is not at all drawn. In this empty stage, the depth buffer is kept to a maximum value, 1.0. How I described your this part. Here I've taken it as 50. Here I've taken it as 50, but they are taking it as 1.0 because they're executing this in the normalized coordinate system. That's why they have taking it as 1.0 and keep comparing with that, because maximum itself is 1.0 in my normalized coordinate system. Initially, all position of depth buffer are set to 1.0, and my frame buffer is what? For all the pixels, what color need to be given, right? In the same way, see here also you can see here, this is my pixel, what color I have given here? I've given a dark blue. Before drawing this, which color I have to keep? I have to keep my background color in all the position of XY. I mean, in my positions, in all the positions of the screen pixels, fine? Background color. This is my initial values with respect to the buffers. Then, now let us see, there is a very important algorithm, or depth buffer algorithm. Where depth buffer algorithm, again the diagram what I have explained you, it is a similar diagram. We will assume here. Initialize the depth buffer and frame buffer so that all buffer positions, for all the buffer positions XY, all the buffer positions initialize what? Depth buffer to 1.0, frame buffer to background color. Now, what you will do for each projected XY, for each XY pixel, what I will do, compare pixel of a polygon. What actually it is done here, I'll just go back and tell you. What actually it is done, polygon by polygon it will process. Okay. First, what they've already told in algorithm, it comes from the backside. So my far plane is 1.0. All the values are stored in 1.0. However, you want to process, you process it. Processing can start from this or from backside. not given how they have done. Let us assume it has come from this part. Okay, processing. So now I have to process polygon by polygon. Fine. I have to process polygon by polygon. The polygon 1 completely I will process. Keep all the XY positions of this polygon valued to 30. Z buffer I'll keep 30. So let us assume this polygon is in color, green color. Okay. Okay, this color, okay, I've drawn down. So this complete polygon is in the green color. So depth buffer ali, I will store everything 330, and frame buffer which gives me a color. I have all XY pixels here. I will store what? Green color. Now I'll come to let me assume this is in red color, this complete polygon. Now I'll process this polygon completely. All the XY positions of this polygon. All XY, Z, depth buffer only, the Z value is stored now what? 20, because it is 20 is less than, sorry. Now let us consider 50 only, okay? Otherwise I have to take different values now. For 1.0, I should take different value. Let us take our far plane, it is replaced to 50 only. So 30 is less than, sorry, 20 is less than 30. All my depth buffer Z value stores 20. Color buffer stores red. Is that clear? And let me keep this color as it is S1. Now the S1 polygon will be processed. All the XY positions of this polygon is stored, Z value stores by 10. And this color will be stored by this some kind of a greenish color. So now you understood the way it stores. Fine. Now, when you see this image here, see this part of XY, this part of XY, this part of XY. Here also polygon by polygon it will store for me. So all this part of XY will not have any change. When it comes to the second polygon, I think only this part, see, this part of XY will compare with the previous polygon of XY. And if I see this is less than compared to the previous of depth color, depth Z value, then I will keep this on my depth buffer. Frame buffer, I will keep this color. Before what color I had this color and this value. Now it has been replaced to this. Now all this again pixel, second polygon pixel is actually processed. Now come back to this now. When I come to this pixel, now all this is processed. My currently Z value for this pixel was this objects. But now when I start drawing the front mobile, this will be changed. The Z value will be changed compared to the previous one, right? So now which color is seen now? Only for the pixels which is in this part is actually changed. Both in the frame buffer and the depth buffer. Hope you have understood. Now let me fast. I have only one slide left. So now you just read this. For each projected XY pixel position of a polygon, calculate the depth Z. If not already known, if you don't have, calculate the Z. If Z is less than the actually stored on this pixel, if that on that pixel position, if the Z value is less, then you keep the current Z value and surface color also should be set. So now what happened? Depth buffer in the new position, I will have a Z value. In this position, XY position of depth buffer, I will have Z value. In this position of frame buffer, I will have surface color. Fine. I will have surface color. Color and Z both is replaced now. After all surface have been processed, the depth buffer contains depth values for the visible surface and the frame buffer contains the corresponding color values for those surfaces. So now, how do we actually calculate the Z value? Given a plane equation we have, because polygon by polygon only I will calculate. If I want to Z, then what was my plane equation which we have seen the previously? Ax plus by plus cz plus d is equal to 0. If you want Z, then you will get this equation. Fine. If you want to calculate the next one, how do you go? We will use a scan line. Why? I am in this position, first position of pixel. If I want to go to the next one, my y will be same because my current scan line is same, right? Only I have to increment my x, right? I will increment x to x plus 1. See here, I will increment x to x plus 1. Okay. When I increment x to x plus 1, how can I replace my value? See, I've multiplied completely. Ax plus ax minus a, all this. Now I've separately. This part is nothing but my z, this equation. This equation, which I can replace it as z minus ac. So this is what I've written here. Z dash is equal to z minus ac, where all the time you can just increment minus ac to the z, which is a constant increment throughout the y scan line. Once you complete here, you will come to the next scan line, that is y minus 1. The next scan, at that time, your y will be replaced by y minus 1 and x will be x itself in the first position. That is your different formula. Hope you have understood this. So both your x and y will be incremented or decremented by 1 whenever is required. Thank you.